Okay, so welcome back. Been a while since the last one, but let's look at functors, applicative functors, and monads in chapter 5 of functional programming in Lean. So functors and monads are both generic types, and if I recall correctly, then a functor basically is just a type that basically has a map method. And well, it says here they are still waiting for a type argument, which is to say, I mean, both of those are like generic types. And so naively, you could say that the functor is something where the contained data can be transformed, and a monad is something that's encoding a program with side effects. But of course, that's not necessarily true. I mean, I guess they're using side effect here in a more general sense, like not necessarily like IO, but also something like option, where the side effect is just that it can fail. But the thing with option is that it has an instance for both functor and monad, so it's both a functor and a monad. Because obviously you can map over like the value of the option, and you can also like chain it to another function using a bind operation. Actually, I believe that this is true for all monads. I think if you have a monad which has a bind operator, you can always define a map function based on that bind operation. Yeah, so the next paragraph again is about these two perspectives of an option. One of the perspectives is that option is basically a data structure, and we can like apply a transformation to the data structure. And like the monadic perspective is that option represents a computation that might fail. And of course, I mean, both of those are true. Yeah, and if I had only read on, I mean, they mentioned exactly what I just said earlier, that every monad is also a functor, which is basically just saying that the monad is a more powerful abstraction because not every functor is a monad, so it only goes one way. And then in between those two, so in between the functor and the monad, there's this thing called applicative functors, which honestly I always found a bit confusing. But the expressive power of an applicative functor is basically in between that of a functor and a monad. So again, every monad is also an applicative functor, but not every applicative functor is a monad. So after the intro introduced us to like the notion of functors and applicative functors, I guess the first sub-chapter is actually about something seemingly unrelated, structures and inheritance. And yeah, it says here that we need to understand that first in order to understand the full definitions of the functor and applicative. So Lean has structure inheritance, which allows one structure to provide the interface of another along with additional fields. And I'm assuming in interface there they include like not just the methods, but also like the pure data fields. And obviously like inheritance is sometimes very useful when you have like a clear taxonomic relationship. But I think it's also kind of a double-edged sword, like it can be overused, as you can see in probably most object-oriented code bases, which is why some languages like Rust don't have inheritance in that sense, at least not inheritance of like struct fields. And some languages like Go have it, but like sort of in a restricted way that's not like the traditional object-oriented way of inheritance. Well, let's find out how Lean handles it. And the example we're going to be using here is a structure mythical creature that only has a single attribute large, which is a boolean. And yeah, as we saw in a previous chapter, like if you define a structure like this, then Lean by default gives you this constructor function called mk, because it's necessary to abbreviate a 4-letter word even further. So we could call it like this, right? Just passing the boolean. And then obviously if you define it like that, then Lean also gives you this like namespace function that's called like by the same name as the attribute that you can use to extract the attribute again from like an object. But I think we saw that you can also just use the normal dot notation like this. And yes, that also works. Okay, and now we can define a monster that extends our mythical creature and basically has an additional field. So obviously one thing I was like immediately curious about is whether it supports like multiple inheritance, and seems like it does, and seems like it also doesn't complain if there's like a conflict. So I defined a house appliance structure that also has an attribute large, and our monster can happily extend both. And if you eval it, it seems to be that the way it's working internally is that it just stores like a reference to a mythical creature, or it stores like a mythical creature, and then in addition the additional fields. What I'm just wondering is what happened to my house appliance. Maybe the syntax is not doing what I think it's doing. So again, it's letting me create the monster just using a creature and a vulnerability without giving any house appliances. Okay, so we can also initialize it like this without explicitly like creating a creature first, by just initializing the fields individually, I guess. Interesting. Yeah, and as we already saw behind the scenes, it's implemented using composition. So a monster basically just has a mythical creature internally, but I guess it is treated as if it was a mythical creature. Actually, let's try this. So I'm gonna try to define a function that takes a mythical creature. And what if we pass this now a monster? Yeah, so it really is like not inheritance in the sense that like object-oriented languages do it with the Liskov like substitution principle, I think it's called. So you cannot substitute a troll for a mythical creature. So I guess really it's just composition with some additional conveniences under the hood. So I guess if I now call to mythical creature, it does in fact work. And interestingly, it also like allows me to convert it to a house appliance. So now I'm wondering, what if I change the type here to create a conflict? Yeah, so when the types mismatch, then the multiple inheritance is going to complain. Because I guess these fields are not like namespaced or anything, so you can like directly, let's undo this, directly evaluate like troll.large, and obviously the only way this can work is with multiple inheritance if all of the paths in the diamond I guess agree on the type. So in some sense I guess it's just taking the union of all of the fields of the other types here, and yeah, if there's like a direct conflict then it will not compile. That's nice at least. Yeah, again, if you read on, they also mention this. So moving up the inheritance hierarchy in Lean is not the same thing as upcasting in object-oriented languages. Yeah, because an upcast, so for example, if you upcast from my custom button to just button, then that button reference will still like retain the identity and the whole structure of my custom button. But in Lean, if you move up the inheritance hierarchy, actually the underlying information is erased. So yeah, as we saw earlier, if we evaluate troll.to mythical creature, we get a mythical creature back, and there's like nothing in the result to indicate that this is a part of a troll. And yeah, we can also initialize these using the like familiar curly brace syntax that most other languages use for structures, instead of the where syntax that we saw above. Yeah, but what does not work is the angle bracket syntax. So here it then, leaks, I guess, the underlying compositional structure. So it's expecting a mythical creature here instead of a Boolean. Yeah, but then you just put another set of angle brackets, and then obviously this inner set is going to call the mythical creature constructor, and the outer set is going to call the monster constructor. As we just saw earlier, the dot notation takes the inheritance into account. So if we call like troll.large, it will implicitly like call the large method of mythical creature. And yeah, this is like a special case in the dot notation. In general, we don't have the substitution principle. So if you use the mythical creature dot large, who in like the type signature takes a mythical creature, right, then we cannot pass a troll here. And actually, I think that these restrictions kind of make sense, because I've seen object-oriented code bases where it becomes like a real mess, because method calls keep jumping through the type hierarchy, through the class hierarchy. So you have some class that calls a method, but then that's overridden by like a child class, like 3 levels down, and then that calls another method. That goes again like 1 level up, and that calls a method that goes again 2 levels down, right? It can get so confusing if you have this substitution principle, and if you like retain the whole like type information, obviously, because at each level you can like override stuff in the traditional like object-oriented languages, like for example Java. And I think that's one of the main reasons why many people like dislike these languages, or at least try to like avoid this kind of inheritance. Yeah, so the thing with the dot notation also works for user-defined functions, not just for the automatically generated accessors. So if we define mythical creature dot small to be the opposite of large, then we can actually call troll dot small, and it will know which function to call. So it will know to like insert basically the conversion to mythical creature here in the dot place, in the place of the dot. 5.1.1 multiple inheritance. Okay, so we're defining a second structure that extends mythical creature called helper with 2 string fields, assistance and payment. And we define one object of type, or one value of type helper, called a nis or nissi, I don't know how to pronounce it, that is not large, assists with household tasks, and is paid using porridge. Yeah, now we're defining a structure, monstrous assistant, that uses multiple inheritance to extend monster and helper. So basically it's gonna be a domesticated monster. And then we can create a domesticated troll who we can pay in toy goats. And I mean, here, that's the thing with multiple inheritance. You always get these diamonds. So, and I mean, just to illustrate this with some ugly ASCII art, it's called a diamond problem because if you draw the type hierarchy, you get this sort of diamond shape. So you have the mythical creature at the top, and then it branches out to monster and helper. And then you get the monstrous assistant at the bottom. So with some imagination, it looks like a diamond, right? Like this kind of shape. And in theory, that diamond problem can lead to problems in this case. I mean, I guess not in Lean, but depending on how you implement it, if you then want to call like a method, like for example large, on our domesticated troll, it's not clear whether you want to call the large that you inherited from monster or the large that you inherited from helper. And I mean, as far as I know, that in C++ you actually like could have different values of large in both of those paths in multiple inheritance because of the way it's implemented, but I guess in Lean it's literally just taking the union of the fields, so we don't actually run into this problem. So in Lean, by definition, it always just uses the first specified path to the grandparent structure. And it says here that additional parent structures field are copied rather than having the new structure include both parents directly. I think what this means is that we're not like literally using composition. So I'm trying to write this out to explain what I mean. So In our monsters assistant, we extend monster and helper. That means we get a 2 monster and a 2 helper. And if it was actually doing this behind the scenes, like giving us a separate monster and a separate helper, then we would actually have this problem, because then the monster could be large while the helper could be small. But yeah, I think what they're trying to say with that sentence is that actually this is not how it's implemented, and it's not going to like redundantly store any fields. So I guess that's what I said earlier when I said that we're taking the union of all the fields. Yeah, so if we look at our constructor of monsters assistant, then we can see it takes a monster, but it does not take a helper. It just takes the fields separately to avoid this sort of redundancy, or getting like opposing values for the same field. So obviously the 2 helper function then needs to be a bit more involved, because the 2 monster can just return the monster from the constructor, but we don't have a helper in the constructor. So if we print out the 2 helper function, we can see that it's literally just creating a fresh helper using our mythical creature that we inherited and the 2 separate fields from the constructor. And it says here that the add reducible attribute has the same effect as writing abref. So I'm not exactly sure what the effect of abref was. I think it had something to do with type checking. Yeah, so definitions written using abref are always unfolded, and if you just use def, then for some parts of the compiler, I guess it's going to be opaque, for example, for overloading resolution. 5.1.1.1 default declarations. Okay, so when we have inheritance, then we can define fields in the parent class based on like computations of the child's fields. So for example, if we define a sized creature that extends mythical creature, we can automatically compute large based on our creature's size. And so this is strictly a default. We can still create a nonsensical creature that is small but has a size of large. Yeah, so it's not preventing us from redefining the default fields. And I mean, obviously, yeah, there's a few ways you could resolve this problem. I mean, you could document it in your documentation. And I mean, obviously, Lean being a proof assistant, you can define a proposition of how the fields are supposed to be related, and then pass the evidence for that in your API. Or, and I guess in many cases this is the right choice, just don't use inheritance. I mean, especially don't overuse it when you can also achieve the result with normal composition, I guess. And the way you would define such a proposition is by using abref for reasons that will hopefully be explained instead of def. Specifying a name like sizes matched, and we get our sized creature as an argument, and we return a proposition. And the proposition is that the value of large is equivalent to computing the value based on the size. Yeah, so note the 2 different equal signs. We have this single equal for the propositional equality, I guess, and the double equal for, I guess, the computational equality. Yeah, so the type of an expression with equals equals is going to be just a bool, and the type of this whole expression is not going to be bool, it's going to be prop, because again of the single equal sign. And yeah, so the reason we're using abref is that it should automatically be unfolded in proofs. And if we do that, then this decide keyword that I think we saw at some point that like tries to automatically synthesize a proof can see the equality. And there's an example for this. So we define this creature called a Halder, which has a medium size. Then we have this proof that the sizes match for Halder, which again we're just going to let Lean decide. And this works, and I guess if I was using def here, it would cease to work. But if I manually tell it to unfold sizes match, then it works again. So yeah, I guess we can see that the abref just causes it to unfold by default. Works again. 5.1.1.2 type class inheritance. So we already saw earlier that in an earlier chapter that in Lean type classes are just structures behind the scenes, and instances of type classes are values of those structures that the compiler is just automatically keeping track of. Yeah, then we just get type class inheritance as an automatic consequence of structure inheritance. But obviously you could also have type classes be a totally separate language feature, like traits in Rust, and then support inheritance just for that without supporting structure inheritance like Rust does. But again, in Lean, they're obviously literally the same language features, so all the stuff that we just saw, like default implementations and collapsing of diamonds and multiple inheritance, automatically also works for type classes. Yeah, so through this system we can get the best of both worlds. We can have our fine-grained, independently implementable abstractions, like for example monads, but we can also have more general abstractions like functors that are then automatically defined if you have the necessary implementation. So I guess it will have, for example, a default definition of a functor if you already have a definition for monad. 5.2 applicative functors. So I guess we already introduced functors at some point in this book, so we don't need to do it here again, even though I had totally forgotten about it. And it jumps straight to applicative functors. But again, a functor basically is anything that has a map method. And an applicative functor then, in addition to the map method, has a method pure and a method sequence, which sounds very similar to monads actually. Yeah, and the pure is in fact the same pure as we already saw in the monad type class, because monad inherits from applicative, and sequence or seek is like map, so it allows us to specify a function to transform the content of the data type. But the special thing with seek that we didn't have with functor is that this function itself can be contained in the data type. Yeah, so this seek function has this type here, where I think f is our applicative instance. So we have this function that's inside the applicative f, and if we pass this wrapped function to seek, then it will give us back another function that as a first argument takes a producer of wrapped values of type alpha, I guess. And that's a bit confusing to me, why doesn't it directly take f of alpha and then it produces f of beta? Because let's see, in Haskell the equivalent would be this operator, the equivalent to seek, I mean, and here we get a wrapped function from A to B, and it returns us a function that goes from a wrapped A to a wrapped B. And I mean, I'm guessing the difference here has something to do with Haskell being lazy and Lean being strict by default. But I don't see how this, why we need this unit type here. Maybe it will be explained later. Yeah, it says here that having the function under the type f allows the applicative instance to control how the function is applied, while functor.map unconditionally applies a function. Yeah, I hope this will become clear later. And it says here the second argument has a type that begins with unit to allow the definition of seek to short circuit in cases where the function will never be applied. Yeah, so I guess that explains the difference with the laziness, because in Haskell, if you take an argument like f of alpha, then that doesn't mean that it has already been evaluated, right? It's only going to be evaluated if you actually use it. But in Lean, by the time that the control reaches our seek function, this argument would have already been evaluated, and thus we cannot then we don't have the freedom to decide to not evaluate it. So I guess that's why it needs to be a function. Yeah, and now they have an example where we can see the value of this short circuiting. So we define an applicative instance for option, where pure is just some and sequence of f of x. Pattern matches f. So f is our function from alpha to beta, and x is our thunk for computing the alpha. And I mean, obviously, if f itself is none, so if we don't have a function in the first place, then we don't need to compute our alpha. We can just throw away x and return none. And in the other case where we do have some function g, so g is just like f unwrapped, like taken out of the option, then we can just call fmap on x. So I guess it's important that both of these are wrapped, so like both f and x could be none. And actually, I mean, obviously we cannot use x directly, we need to pass this unit here to actually then evaluate it. So now this expression will be evaluated to like an actual option value, and then we can just call fmap using the fmap operator. I guess in Lean it's not even called fmap, it's just called map. And obviously in the case of except we have like the exact same optimization that we can make. In case of errors, we don't need to continue on with the computation. We can just short circuit. And obviously, I mean, this is something that the monad instance did as well, and the monad can do as well. So the point with applicative is, I think, that it's a more general structure. So even stuff that is not a monad can be an applicative. But honestly, I hope that this chapter will have some like more real world examples, because again, in both of these cases, you could do exactly the same thing with the monad instance. Yeah, and the short circuiting only depends on the surrounding structure and not on the function itself. I mean, obviously we cannot inspect a function. It could be any function, right? So we cannot really make any decisions based on the concrete function. So monads can be seen as a way of capturing the notion of sequentially executing statements into a pure functional language. And this also captures conditional execution. So whether one statement is executed can depend on previous statements. Yeah, so in the type of bind, we can literally see that we take the value of the previous computation, which is called alpha here, into account when computing the value or the next computation or the next step to execute, basically. Yeah, and if you like chain these uses of bind together, I mean, in most cases you're going to use do notation for that, then bind is powerful enough to implement the same control structures that we know from imperative languages like conditionals and loops. And using the same analogy, applicative captures function application in a language that has side effects. So it's going to evaluate the arguments from left to right, and the side effects are also going to be performed in the order in which the arguments are evaluated. But what we cannot do in applicative is custom short-circuiting operators that depend on the specific value of an argument. Yeah, so if there is any short-circuiting, I mean, you can even see it in the type, then this function has no control over it, right? Only the sequence function from the applicative instance has the control over whether or not to perform the next step. Yeah, to save ourselves the trouble of invoking seek directly, there's a handy operator, which is an asterisk in angle brackets that we can use to invoke it. And that operator, I guess, isn't just an alias, it will also wrap the second argument in a lambda. So if you have e1 asterisk e2, then that's syntactic sugar for sequence e1 and then a thunk that computes e2. So lean is curried, right? So there aren't really multiple argument functions, that there are just functions that take a single argument and then return another function. And apparently this is essential for how seek works. So if the first argument to seek is awaiting multiple arguments, then the result of the seek will be awaiting the rest. So I think they're just describing currying here. So if we use sum plus, then we get the type option of natural to natural to natural. And if we provide one value, so sum plus asterisk sum 4, then the resulting type is option of natural to natural. So it's now just awaiting one argument instead of two. Yeah, not every functor is applicative. So let's, for example, define a type pair that works like the built-in type prod that has a first value and a second value. So it's notable here that pair takes two type parameters, right? So the type of pair is type to type to type, so it takes two types. And obviously pair alpha, so if we fix one of the types to be alpha, then only has the type to type, which is exactly the signature we need to define a functor. So we can define a functor of for pair of alpha, where our map function just maps the second field. And there's nothing wrong with this functor, right? It's a perfectly valid functor. So obviously we can map the ID function into it and without changing the actual value of the point. And we have this sort of associativity law. Yeah, I guess we can see that this dollar operator is right associative, right? So we first evaluate this part and then apply the f. And obviously it's the same if we start from the other direction, so first composing f and g and then applying it to our point. And what we can see now is why our applicative instance cannot be defined for our pair, because we need to define this function pure. I mean, sorry, not for pair, but again, remember we're defining the functor for pair of alpha, so we're kind of fixing the alpha. And for our pair.pure, the type signature would be that we take a beta and we produce a pair of alpha and beta. And obviously, like knowing nothing about type alpha, we cannot make up a value of alpha like out of thin air, right? Alpha could even be like a type that's uninhabited, right? That has no values in theory. I mean, Lean allows stuff like that. It's not like in Go, for example, where every type has like a 0 value. So there's literally actually no way we can define pure. Yeah. Again, literally reading on, we see that they bring this exact argument because the caller could choose alpha to be the type empty, which has no values. I think what you could do is like define a trait. Maybe there is such a trait, like to get a default value for a type, and then sort of restrict it. So you can say like implement a type class for all pairs of alpha where alpha is default initializable, right? And then it would work with applicative, right? Because then we could define pure, pretty sure. 5.2.1, a non-monadic applicative. Yeah, so when we are validating user input in a form, it might be beneficial to not just like quit on the first error, but actually give all of the error messages so that the user can correct all of them at once. Yeah, I mean, one way you could do it is you have your validation routine, for example, that checks that the textbook contains a number. So you could just make a function that gets like a string as input and a number as an output, and if it's not a valid number, it throws an exception. But that would then terminate the program, so then we would be terminating at the first error. And obviously we can manually do this kind of validation using if statements, but it would be nicer if we had an API like to abstract over that. And we can create this kind of API by creating a applicative functor called validate, which works similarly to the accept monad, but different, or like unlike the accept monad, it allows multiple errors to be accumulated, and it then guarantees that we cannot just forget 5.2.1.1 user input. So we have our raw input, which is a name and a birth year, both as strings. And the logic we need to implement is check that the name is not empty, the birth year must be numeric and non-negative, and the birth year must be greater than 1900, and it cannot be in the future. Okay, but before we go on implementing the business logic, they want to introduce a new feature called subtypes. 5.2.1.2 subtypes. So we're going to create this structure called subtype, which takes a type alpha, which should be inferred, and a function from alpha to a proposition. And it's going to just store a value of type alpha and a property, which is the proposition based on the value. And I guess if it's a function that goes from a value to a proposition, then it's called a predicate. So the fields are, or like the interpretation of those fields is then that we have a value of type alpha and evidence that the value satisfies the predicate P. Because if it doesn't, then you couldn't like construct this proposition, I guess. And Lean has a special syntax for this subtype type. So if we have our proposition P of type alpha to, our predicate P of type alpha to proposition, then the type subtype P can be written using this notation here, where we say we have our X of type alpha and then double slash predicate of X. Or if we can infer alpha, then just X. Is this even a slash, or is this a... Yeah, this is a slash. I was wondering if it's like a pipe and looks like a slash because it's in italic or something. So in the earlier chapter we saw how to represent positive numbers as inductive types. I mean, I guess basically you just start like you have a constant 1 and then a successor function. But there's like a disadvantage to that approach because, or like the structure is like exactly isomorphic to, for example, the structure of NUT. But NUT is like a special type that's treated specially by the Lean compiler to like for additional performance, because obviously literally representing natural numbers using an inductive type, which is basically equivalent to using a unary encoding of the number, is, I mean, horribly inefficient. So Lean's going to treat NUT specially, but it's not going to treat our own positive number type specially. But if we use the subtyping feature, then we can get the efficiency of NUT, or like the same runtime representation, while at compile time ruling out the number 0. Okay, so yeah, we can define our positive numbers like this. And if we go to definition, we actually see that this is implemented as a macro. So I guess it's not like hard coded into the compiler itself, but somehow implemented in the standard library. Yeah, so we can define an instance of our fastPos type by using the angle bracket notation. And I guess the curly bracket notation also works. So yeah. So if we define our offNUT instance that we can use numeric literals for the fastPos type, we obviously have to define it for this successor of n, because n itself could be 0. And then somehow we're using simp here instead of decide. And I guess this is because decide requires a concrete value, and we don't have a concrete value, we just have n plus 1 at this point. So at this point now we can just use a normal literal as a fastPos, and if we use 0 it should scream at us. Yeah, so this is a bit of a double-edged sword. So we get a very efficient representation of our validation rules, but we sort of transfer the burden of maintaining the rules to the users of the library, because now they have to prove that they're not violating any invariance. And if you instead enforce the invariance by just writing like algebraic data types that make the construction of an invalid state impossible, then there's no proof required, right? It's implicit in the program, but I guess it's a trade-off, because, I mean, especially in this case of positive numbers, it would lead to a horribly inefficient implementation. I mean, you don't have to implement it like unary. You could implement positive number type like as a structure that has a natural number field and always like implicitly add 1 to it, right? But I think it would still be less efficient than just having like literally the same runtime representation as the natural number itself. Yeah, and they say here that this is something that is a good idea to use internally in your library, but maybe not expose through your API. Instead have some like functions in the API that ensure the invariance. So we're defining this function here, nut.sFastPositive, which takes a natural number and returns an option of fastPositive. And Lean has this special syntax where we can give it a proposition in an if statement, right? And bind that to a name. So basically, I mean, this is a decidable proposition. So at runtime, we can literally just evaluate it to check the proposition. And then at compile time, we get this h as like evidence that the proposition holds. And actually, I mean, here we're not using it in the else branch, but it says that we could also use it in the else branch as a proof that the proposition is false. So this h would be in scope in the else branch as well. 5.2.1.3 validated input. So we are defining this structure checked input, which on the type level is parameterized by the current year. So I guess it's a dependent type because it depends on this constant. But yeah, I mean, basically it's const generics, right? So we have our name, which is a non-empty string. And I mean, I guess you do have to admit that this notation is kind of nice. So, I mean, I think it's kind of obvious, right? We have our string n, where n is not the empty string. It's basically like in mathematics a set comprehension. I guess this is where they got the syntax from. And the birth year is a natural number that's required to be bigger than 1900 and not bigger than the current year. Now we're going to represent our validate type using an inductive definition, so basically like an enum. And validate is going to take two type parameters, epsilon and alpha, and have two cases. In the OK case, where it consists just of like an alpha, right? And then there's an errors case where we take a non-empty list of error values, and yeah, we get our validate of epsilon and alpha. The only difference to accept is that we are allowed to have more than one error. So now we can define a functor instance where the errors case is just passed along, and the OK case causes our value to be mapped using the provided function. And now when we define the applicative instance, we can see where it differs from except, because we are not going to terminate at the first error, but instead accumulate all errors from all branches. So let's see, the pure is just OK, and the sequencing operation is going to first check whether we even have a function at all. If we have a function, like we unwrap f into g basically, and then just call the map function of the functor. And if we have errors, then crucially we are still going to evaluate our next argument, right? We're not going to short circuit. But even if it like is okay, we're then going to ignore the okay value and just pass along our errors. But if there are further errors, then we are going to concatenate those errors to our existing list of errors. So we're going to define this helper function report error, which takes a field, which is just an alias for a string, and a message, which is a string, and gives us a validate with our error being tuple of field and string, and the result type alpha. And yeah, we're just going to return the errors variant and call the constructor for the non-empty list. So now we need to implement the individual checking procedures. For check name, we write a function that takes a string and returns a validate instance with the result type being like non-empty strings. And yeah, we just use this same technique here where we bind the proposition in an if statement, or an if expression rather, and now in the else branch we also have this name in scope, and now it's like the negation of our proposition, so that name is not the empty string. So now we can construct our validate instance using that evidence. And sometimes we don't want to run all the checks. I guess if the birth year is not even a number, then it doesn't make sense to check whether it's bigger than 1900. And for that case, we can define our and then function. And then I begin wondering what the difference is to like a normal monad instance with a bind function. But let's see. So we have a value, which is like wrapped in a validate instance, and then We have our next function, which takes the unwrapped value and returns a new validate instance. And the result is, in fact, another validate instance. So as far as I'm seeing this is exactly the type signature that a monad instance for validate of epsilon would have. Okay, and that's also what they're saying here, that purely from the type signature, we could just use this as the bind of a monad instance, but apparently there are good reasons to not do that. And we will apparently see the reasons in the next section that describes the applicative contract. So now we define a check year is nat function, which takes a year as a string and returns a validate instance of a natural number. And we're doing this by trying to just parse it as a natural number. And in case we get none, then we return an error, and otherwise we just return our wrapped natural number wrapped in a validate value. So now we can finally check the birth year. If we have already that the year is a natural number, then we can return a validated birth year. And we're using the same technique as all the time by just using an if statement and binding the evidence to a name. And here I'm not really exactly sure what this syntax after simp means. But yeah, in the failure cases we can report the errors, and I mean this function is written in a way that it can report at most one error. And now using our sequence operator we can combine our individual checking functions. So by saying by calling the constructor function of checked input. So first we basically need to lift it up into the context of validate using the pure constructor, and then we can call the sequence operator on it, first giving the name, and then using our custom bind function to first check that the birth year is a natural number and then actually validate the birth year. And we can verify that it works correctly and gives the correct error messages. And I mean, crucially gives multiple error messages in case there are multiple errors. And the key applicative advantage here over the monad type class is that in the bind operator of the monad, we must receive a value from the first step. So if the first step failed, then the monad implementation has no choice but just short circuit. But yeah, in case of our validation, that's not what we want. We want to run the rest of the program anyway. Yeah, and the applicative sequencing operator can run both of its arguments before recombining the results. So it doesn't force this sequential execution like monads. And I think, I mean, technically, using the applicative sequencing and Lean being a pure functional language, you could imagine an applicative instance that runs, that evaluates the arguments even in different threads. So more powerful abstraction like monad increases the flexibility for the API consumer, but decreases the flexibility for the API implementer. So because with a monad instance, you don't know which parts are independent of each other, which parts you can parallelize. 5.3, the applicative contract. Yeah, so similar to other type classes, there's some rules that we need to follow to implement applicative. So the first rule is that it needs to respect identity. So if we lift our ID function into the applicative context and then apply it using our sequence operator, we just get the original value back. Needs to respect function composition. So if we lift our surprised face function composition operator, into the applicative context. So basically we're wrapping it right in our applicative implementation and sequencing it with U, V, and W. Then that's the first thing as then it's the same thing as first applying V to W and then applying the result of that to U. And third, that sequencing pure operations should be a no-op. So if we take a plain function and a plain value and we lift up both of them, or like we wrap both of them in an applicative and use the sequencing operator, then that's the same as just doing the computation outside of the applicative context and then wrapping it. And fourth, the ordering of pure operations doesn't matter. So if we sequence U with a pure X, it's the same as lifting this lambda function, which takes a function as an argument and applies it to X, and sequencing that with U. I think that's like the least intuitive of all of them. So basically U is a wrapped function, right? And we're like unwrapping U and applying it to X. And this should be the same as defining this function here, which like basically takes the unwrapped function of U as an argument, right? And applying that to X. So I think what it means by the ordering doesn't matter is that it doesn't matter whether we first like lift X into our applicative and then do the computation, or whether we first do the computation and then lift the result into our applicative. I think what would be helpful for this would be like giving an example of a applicative implementation where like this rule isn't true. Anyway, now they go on to check the applicative option instance, and I think I'm going to skip that because these proofs tend to just be like expanding the definition and not very like actually helpful. 5.3.1 all applicatives are functors. The two operators for applicative are enough to define map. So given our type class instance of applicative for f and a function g from alpha to beta and a wrapped value alpha, we can get a wrapped value beta by just like literally lifting the function into the applicative context and then calling the sequencing operator. So I mean, this is pretty clear, I think. So of course we need to check that this actually satisfies the rules that we had for functors. And the first rule was that if we map the ID, then we don't change the value, which follows from the first rule for applicatives, which I mean, yeah, states essentially the same thing. So if we substitute like our definition for map, right, then we get exactly this rule. The second rule of functor was, I guess, this sort of distributive law with the map function and function composition, that mapping f composed with g over x is the same as mapping g over x and then mapping f over the result of that. Now if we unfold the definition, we get that pure of f composed with g sequenced with x is equal to pure of f sequenced with pure of g sequenced with x. And then we can essentially use the rule that the applicative functor respects function composition to show that. So this justifies that for an applicative, we can say that it extends functor, because every applicative is a functor. And yeah, for the map here, we can give a default implementation based on sequence and pure 5.3.2. All monads are applicative functors. So monad already requires pure, as we saw, and we can use the bind operation to define the sequence operation. So if we have our type class instance of monad for type M, and we have a function that's wrapped in M from alpha to beta, and a thunk that computes an M of alpha, then we can compute an M of beta. So we first just apply F, and then we apply the argument, and then we return the result. So this is like literally straightforward. Of course, like the do notation is then going to be like in behind the scenes translated to a bind operation that will actually do all the magic of like handling the underlying monad correctly. And obviously in this case as well, we technically need to check the contract. And yeah, I mean, Lean being a functional language, we can like do these kind of proofs by just like doing like equational reasoning on programs, right? So the first step is to desugar the do notation and like explicitly inserting the bind operator. So pretty trivially it follows by just substituting like the laws and the definitions that we respect the identity function. Next we need to check that it respects function composition. And yeah, I mean this is also completely technical, so I think I'm going to skip it. Next proof is to check that sequencing pure operations is a no-op. And then to check that the ordering of pure operations doesn't matter. And now that we have justified that the laws are satisfied, we can define monad as an extension of applicative, where we just give this default definition of the sequencing operation that is the same that we already saw above, just without do notation. So if we just define a monad type class for a type, we get applicative and functor for free. 5.3.3 Additional stipulations. And so obviously we could also have defined these instances manually, and maybe there are good reasons to do so, but one thing you should keep in mind is to not differ from the default implementation's behavior. So behaviorally, if you, for example, implement the sequence operator manually for a monad, it should behave the same as the default implementation, so that you can in the end refactor between like applicative and monadic style code without changing the meaning of the program. And this is why our validate instance has an and then that even satisfies the monad contract, but we cannot define a monad instance because the behavior of our sequence operation for validate is not the same as the behavior of the sequence operation that could be generated using our and then function. Because for validate we specifically didn't want the short-circuiting behavior of the monad. Yeah, so if we look at an example where they differ, so not fun is supposed to be a function from natural to string, but actually is an error, and not arc is supposed to be a natural number, but it's actually an error. If we apply not fun to not arc, using our applicative sequencing operation, then obviously in the end both errors are going to be reported. But using the sequencing operation that we would automatically generate from the hypothetical monad instance, we can see that it would short circuit and only report the first error. So that's why we didn't, or they didn't define a monad instance for validate, even though it would like totally be possible, right? 5.4 alternatives. 5.4.1 recovery from failure. So we can use validate in situations where there is different like acceptable forms of input. So they have this example here where all human users must provide a birth year that is 4 digits. Users born prior to 1970 do not need to provide names due to incomplete older records. Users born after 1970 must provide names. And companies should enter firm as their year of birth and provide a company name. No particular provision is made for users born in 1970. It is expected that they will either give up, lie about their year of birth, or call. The company considers this an acceptable cost of doing business. That is sadly relatable. The following inductive type captures the values that can be produced from these stated rules. Okay, so we have a non-empty string type. We have an inductive type legacy checked input, where there's 3 cases: human before 1970, human after 1970, and company. And before 1970 can be any year as long as it has 4 digits. After 1970, well, can be any year also in the future, I guess, as long as it's bigger than 1970. And company has literally just its name, nothing else. And so this is going to make our validator more complicated because now we need to check all cases. And we could do this using nested if expressions, but it could be easier to just define the cases separately and then combine them, right? And that means we might need to recover from a failure while preserving error messages. So we're defining this combinator validate dot or else, which takes a value a, which is of type validate alpha, a value b, which is also a validate alpha, and we get in the end a validate alpha, and obviously all validates need to have the same error type, epsilon. And if a is okay, then we just return it. If there are errors in a, then we try with b. So since b is a thunk, we need to provide this empty tuple here. If b is okay, then well, we just return it. But if there are errors, then, and this is the special case, we concatenate the errors from both branches. And actually Lean even has a built-in syntax for this kind of pattern, which is called or else, where you have a value alpha and a thunk that evaluates to an alpha, and you give an alpha as the result. And you can use this pipe operator in angle brackets as a shorthand for calling this type class. And again, the operator will create the thunk for you, so it will create like a lambda expression around this expression e2 automatically. So if we create an instance of or else for our validate, where we define our or else to be validates or else, then we can use this syntax to combine our validators. So we define another helper function, check that, which takes a condition, which is a boolean, a field, and a message. And if the condition holds, then we just return a unit value, and otherwise we report an error. And now we define our check company function, which takes a raw input and returns a validate of with again, field and string tuples as errors and a legacy checked input as the value. And our constructor here is throwing away the first value, which would be the year, which for the company carries no information. Just like takes the name of the company, and we call this check that with the condition that the birth year is equal to firm, and we check that is just going to return a unit, which is then matched against this unit here, and then yeah, we call check name on the input.name. And now we can simplify this definition using the stuff we learned about. So this case of ignoring one argument in the sequencing operator is actually common enough that there's a separate operator for it, which is asterisk and the greater than sign, which also has its own type class called seqWrite. And again, also does this thing where it wraps the second expression in a thunk to like simulate the lazy evaluation. And we never need to like actually define this seqWrite operation because there's a default implementation in terms of seq. So if we have a wrapped value of type alpha and a thunk which gives us a wrapped value of beta, then we can just use the sequencing operation, ignore the A argument, and just like unconditionally return the B argument. So with that we can simplify our check company function. So we just say check that the birth year is equal to firm, and I guess it will do this part but ignore the result, and then like wrap the rest of this into a thunk that like takes a unit so that we match with this type here, and then just return like the result of doing this, but obviously while preserving the errors from checking the first part. And then we can simplify this even further, since we already know that pure F sequenced with E is the same as just using the functor map. And then we get this slightly simplified definition that doesn't use the pure here. Now we can define a general purpose helper function for checking subtypes, which will take an implicit argument alpha, which is a type, and a value of type alpha, a predicate over alpha, an instance of decidable, which I guess means that it can be automatically decided, I'm not sure. And then an error of type epsilon, and then we get a validate instance with the value being a subtype of alpha that satisfies the predicate. And here it's important that we put decidable after the P and the V are already in scope, because otherwise it would like create implicit arguments named P and V. And we need this decidable instance so that we can use the if syntax to check it. So I guess this really is then decidable in the like theory of computation sense, so that there is an algorithm that decides the preposition, the predicate. So then we can use this check subtype to handle the case human before 1970 and also human after 1970. And in the end we can combine the validators using our or else instance. So either it's check company, or it's check human before 1970, or it's check human after 1970. So in the successful case we can see that it works. We get like the company case here, or the human before 1970 case. And in the worst case, we get all of the failures. So if we have exactly 1970 and have an empty name, then we get that name is required. Birth year must be less than 1970, greater than 1970, and then again that name is required. So honestly, this would, if this were a real application, this would be a pretty confusing error message. So I don't know if we actually gained that much from this exercise, but yeah. 5.4.2, the alternative class. Many types support a notion of failure and recovery. So in an earlier section we already had this many monad, and option I guess is also an example. And in both cases you can just fail without supplying any reason. And there's this type class called alternative that describes applicative functors that have additional operators for failure and recovery. So in the alternative class, we can just here construct a failure without having to provide any reason. And we have this or else, which is I guess the same as the or else type class, where we can combine two values, again a lazily evaluated second value, to recover from the failure. Yes, if we implement alternative, we get the or else instance for free. And for example, for the option type, we can just say that failure is none, and or else just returns the first sum value, and obviously in the none case it then goes to the second value. In the case of our many example, we can define or else to, like in the none case, just evaluate the second argument, and in the more case we actually keep both sides. And if you have an implementation of alternative, then you can use this useful guard function, which takes a type class instance of alternative for a type class f and a proposition p that needs to be decidable, and it gives you a unit value wrapped in f, which if p is true, then it will just be like a unit, and otherwise it will be a failure. And you can use this to short circuit your execution. So in this example we define a many.countdown function, which basically is going to contain all values from 1 to n, where n is like a supplied argument. And then we can define an even divisors function, which takes a number n and returns many natural numbers. And we use do notation and assign k to be the countdown from n plus 1, so from 1 to n, I guess. And we guard with the proposition that k needs to be divisible by 2 and n needs to be divisible by k, and then we just return k. And since this is running in the many monad, it will then like find all such values k that satisfy these conditions. And the short circuiting behavior will ensure that if like this fails, then this one isn't even evaluated. 5.4.3.1 Improve validation friendliness. So we already saw that the errors returned by validate programs that use the alternative operator aren't that useful, because it just returns all errors that can be reached at all through some code path. And maybe we could improve this with a more structured error report. So the first step would be to replace the non-empty list in the validate.errors constructor with a type variable, and then like update our instances. Let's make it like an implicit type, I guess needs to be type to type, and then we can define this maybe. Okay, require only that there be an append epsilon. So I guess they don't want us to introduce a new type variable, but just use the epsilon as the appendable, which means just going to be, and I need append epsilon. For instance, I also need, okay, I thought it would be enough to just say, okay, epsilon needs to implement append, and then we can give an or else instance. I don't get this error at all. Somehow this is about the order here. So when I have the append here as the last argument, the instance, then it doesn't work. If I have it as the first, then suddenly everything works. And I wonder if I need to explicitly have this. No, it's enough if I have, like saying for all epsilons that have an append instance, we can give this or else instance for validate of epsilon and alpha. Okay, so we're supposed to define a function, map errors, that transforms all of the errors. Okay, so we take our validate and our mapping function. We match on V. In the OK case, we just do nothing, and in the errors case, we map the errors. Yeah, simple enough. Now we need to use this type 3 error to rewrite the validation system to track the path through the alternatives. So then we also need to define a report function. I wish they had like some file available for download with all the definitions necessary to solve the exercise. I'm just having to copy paste all of this. Oh, okay. So I just copy pasted the definitions from the chapter. Now we need to replace the error types. We want our 3 error here. Why is this not working? Change the type. Check name, still missing. What's the error in the... I cannot get this to work. Somehow with .ok it's working, but because there was no append bound on the epsilon, I guess. Okay, what's now the issue? We are missing and then. Okay, the next error is we need to refactor this check. First of all, we can use a 3 error here. And then we need to refactor this to be dot field. Okay. Map errors. So, how do we print again? I don't know how we can print something that implements wrapper. I mean, like this, it looks pretty ugly. What if we cannot do this? I forgot how we get the string representation of something that implements like the wrapper. AI is certainly useless. This doesn't help. There has to be a way to do this. I don't know how. Just want to print the result and not have these, you know, errors. These new lines printed as literal new lines. How hard can it be? There has to be some sort of operator where I can just like force it to use the wrapper instance, right? Anyway, I guess the only way we can do now is ignore it. Just print the errors and the thing is now, so far we're not tracking the paths and we cannot like print the representation of our successful. Yeah, so I think that in the check legacy input we need to call the map errors and then supply the path that is producing the error, right? And then it should say, well, yeah, then we can see that the errors for check company are these and the errors for check human before 1970 is this error and so on. I'm more annoyed that I forgot how to use this string interpolation with types that implement wrapper. How hard can it be? We have a wrapper function which returns an std format. But then, okay, this works. I thought I tried this before. So if we, for example, type a name now and use a valid year, then yeah, then it's actually printed. Okay, that's just as easy as calling the wrapper function. Nice. Chapter 5.5, Universes. So in the interest of simplicity, so far we have skipped a feature of Lean known as universes. So a universe is a type that classifies other types. So I guess a universe is what you would call a kind in Haskell, right? Values have types and types have kinds. And I guess in Lean then values have types and types have a universe. Yeah, one of the universes is type, another one is proposition. And type classifies ordinary types like natural numbers or strings or functions between these types. And also stuff like IO of unit. And proposition classifies, well, propositions that can be true or false, such as that the string Nissi equals the string elf, or that 3 is greater than 2. And the type of prop is type, which confuses me honestly. I mean, so the type of type is type 1, that makes sense, and the type of like nut is also type. So nut is on the same level as prop somehow. For technical reasons, more universes than these two are needed. Especially that type cannot be a type. I mean, because this would lead to a paradox, right? There's this like famous paradox in set theory, which is like basically based on the question whether like the set of all sets contains itself. And if type was itself a type, I think you would run into similar sort of paradoxes. And since Lean is a theorem proof, obviously we cannot have like a logical contradiction. So the formal argument for this is known as Girard's paradox, which is related to a better known paradox known as Russell's paradox. And I think that's the one that I meant, which was used to show that the early versions of set theory were inconsistent. So in these versions you could define a set by a property. So you could define a set by the property that something is a set, and that would then give you the set of all sets, I guess. Yeah, and then you have the set of all sets, which obviously has to contain itself because it is a set. But then what if you make a set of all sets that do not contain themselves? So basically like this, right? You have a set. Well, I guess you need to require that you have S is a set and S does not contain itself, right? This is the set that we're talking about. Yeah, so this set would, for example, contain the set of red things, because the set of all red things is not itself red. It does not contain the set of all sets, because we already saw that the set of all sets contains itself, but does it contain itself? So like if we name this set A, then the question is A in A. And there's like two possibilities, right? So if it yes, then well, then we know that if A is in A, we know that A is a set, and that A is not in A, right? We know that A not in A, which is a contradiction. And if we say, well, A is not in A, then we know that, I mean, A not in A, but A is set, which by the definition of A implies that, well, A has to be in A, which is a contradiction, right? So, and that's the type of thing that they're trying to avoid, because this makes your whole theory inconsistent, right? If you can create a contradiction, you can prove anything. Yeah, and one way to remove this paradox is to like restrict the ways in which you can define sets. And I guess, I mean, Lean is restricting it by having this notion of universes somehow. Let's see. Yeah, so in dependent type theory, if we assign the type, if we assign type as the type of type, then we get a related paradox. And to avoid that, the only thing we need to do is to ensure that the type of type is not itself type. And that's why we're just like counting, right? So if you see that the type, if we check the type of type, then we will get type 1, and then the type of type 1 is type 2, and the type of type 2 is type 3, and so on. And if you have a function, then it will be in the smallest universe that has both the argument type and the return type. So a function from type to type is a type 1. And if you have a function from type 1 to type 2, then that is a type 3. And the exception to this rule is that if the return type of a function is proposition, then the whole function type is proposition, even if the argument is in a larger universe. And this means that predicates over values that have ordinary types are in proposition. So we have this function here that takes a natural number n and returns a proposition that n is equal to n plus 0. And let's see. Yeah, this is then a proposition. And even though type is a type 1, if we have this function here that goes from type to, well, 2 plus 4, 2 equals 4, it's also a proposition. 5.5.1 user-defined types. So you can declare your own types to inhabit a particular universe, and Lean will check that your type avoids paradoxes by being like in a large enough universe that prevents it from containing its own type. So if we define a custom list, my list, which takes an alpha, which is a type, and then say that my list of alpha is itself a type, then we cannot construct a list of types with that, because then the whole thing would have to have like type 1 as a type, but we said that the type is supposed to be type. And if we say that the argument itself is type 1, which means that in theory we could have a list of types, but then it then Lean rejects like the whole definition. But I mean, we declared that the type of a mylist, like a parameterized mylist type, is itself type, and that's like a lower universe, so that would be invalid. I think this is what the error message is saying. Yeah, so the recommendation here is to start with a data type that's in the same universe as the largest of its arguments. And when Lean rejects it, then just like increment the type universe. 5.5.2 universe polymorphism. Now obviously, I mean, if we did this for every like level, if we defined a mylist of type 1 and type 2 and type 3, that would just be code duplication. And to avoid like copy pasting the definition, there's a feature called universe polymorphism. And then we can only write a single definition, and it can be instantiated for all of the universes. The Lean multiverse. Yeah. Yeah, so just like a normal polymorphism where we have like variables to name the types, now we have variables to name the universes. And it's conventional to call these U, V, and W. So if we define it like this, with by just saying type U, then I guess it is universe polymorphic. Now we can use it with natural numbers, and we can also make a list of types. And we can also make a list of functions from type to type, so basically a list of generic types that contains the type itself. And this seems like it's just reintroducing the paradox, but in fact it's not, because we now have just like a mylist in each universe. So I guess that this mylist and this mylist are not in the same universe in the end. And the notation for this is to write a dot and curly braces and then the universe level. Yeah, so we can see the mylist of list is of type mylist in universe 1, and then the element is of type mylist in universe 0. Yeah, and if we take multiple types, then we should also use multiple variables to not restrict ourselves too much. Because if we define it like this, using the same variable, then we cannot create a sum type of string or type. But if we use like U and V and then use the max of U and V for the result, then now we have the maximum flexibility. And I guess we can't do like arbitrary arithmetic or anything with these levels here. Like max UV is literally pretty much the only thing that's allowed. We can take the max, we can like increment it, we can use a concrete level variable or like a hard-coded level value, and that's it. 5.5.2.1 Writing universe polymorphic definitions. Yeah, so far the versions of like list and sum that we saw defined in the book aren't the real versions that are in use in the standard library, because the real versions are always universe polymorphic. And yeah, the guidelines for writing universe polymorphic types is, as we already saw, the type arguments should have different universe variables, and the type of the whole expression, or rather like the universe of the whole type itself, then has to be like the maximum of all of those universe variables or greater than the maximum. And generally you should put types into the smallest universe where possible, because that makes it like the most flexible to use. And the non-polymorphic type can just be placed directly in type 0. 5.5.2.2 prop and polymorphism. So we saw that like type and type 1 and so on describe types that classify programs and data, and prop classifies logical propositions. So a type of a type in prop describes what counts as convincing evidence for the truth of a statement. And the difference between like prop and the normal type is that we don't really care about the value. So it doesn't really matter which evidence we provide that a statement is true. We just care that it's true and we prove that. But if you have a program that returns a natural number, then obviously it's very important that it returns the correct natural number and not any random natural number. So prop is at the bottom of the universe hierarchy, and the type of prop is type. So I guess that means that a proposition is just like a normal type, basically. We can have a list of propositions, for example. And that list would be in the universe 0, right? So like the same as if you just had a list of numbers. And behind the scenes, prop and type are united into a single hierarchy called sort. So prop is the same as sort 0 and type 0 is then sort 1. Which means that type u is the same as sort u plus 1. And yeah, sometimes I guess you may see this in error messages. And having proposition as sort 0 apparently allows one more universe operator, which is this IMAX operator, making our lean multiverse even more cinematic. And I guess IMAX of u and v is 0 when v is 0, or the larger of u and v otherwise. Yeah, and this allows implementing the special rule that we had, that if a function results in a proposition, then the resulting type is also a proposition. 5.5.3 Polymorphism in practice. Yeah, so the remaining definitions in the book will use universe polymorphism. And yeah, this will also enable us to give the actual definitions of functor and applicative and monad. 5.6 The complete definitions. So yeah, I mean, definitely an interesting chapter for me. Like when I read these kind of materials about functional programming, I'm always left wondering a bit how this stuff like applies to the real world. Like sure, I understand all of the toy examples and all of the definitions, but um, yeah, I guess I've never really, or like, you know, I've never read an actual code base that uses all of this stuff to solve like real world, like not just mathematical problems. And I mean, when you actually go to like check out some program that does something cool, like for example in Haskell, there's stuff like xmonad or pandoc, right? But if you look at the code bases as a beginner, that can also leave you quite confused, I think. So I would really like if the book had like a little project as an example that actually used some of these features, like, I don't know, the command line to-do list manager or something like that. But yeah, enough rambling. Guess see you next time. The next topic is going to be monad transformers. Also very interesting topic.